Alright, this is Dr. Marion Carroll, and we are continuing with Chapter 6 in the pre-nursing program, biochemistry, organic chemistry, and we last talked about stereochemistry. And I think we're going to continue in Chapter 6. I think this is Part 4. If I recall my previous notes, this will be Part 4. We're going to cover a number of reactions of alkanes. And we'll begin with a description of combustion. Okay, complete combustion. And this involves taking an alkyl compound, say methane, and whenever you burn compound, you're adding oxygen, and of course that will produce water and oxygen and a substantial amount of heat or energy. Okay. Now, one of the first things you have to do when we're looking at this is to balance the equation. And all complete combustion of alkyl groups, depending on, could be at any length, H8, any size, could also be cyclic compound, like what is this, 1, 2, 3, 4, 5, cyclopentane, C5H10. So any number of these alkanes, when they are burned, will produce CO2, water, and energy. And in order to balance, we want to, of course, count up the number of elements on one side to make sure they're equal to the number of elements on the other side. And there's a general way of doing this whenever we're looking at hydrocarbons, we're burning them. We can use this general equation to determine, based on the number of reactants, the moles of reactants, what the moles of product will be. So we have X, Y, and Z, and we can determine what Z is simply by taking what X is, which we would know, on the number of carbons in the reactant, plus 1/4 Y, which are the number of hydrogens in the hydrocarbon. This sum will give us the number of oxygen, of moles of oxygen required to generate, there should be a plus sign, to generate CO2 and water. Another reaction of alkanes involves a radical substitution. Anytime you react an alkane with, let's say, a halide, that is bromide, or chlorine, fluorine, any of the halogens, these are group 7A. You're going to generate a carbocation or carbon radical. And so let's say chlorine, in the presence of ultraviolet light, will produce chlorine radicals. Also, if we take our methane and treat it in the same way, we'll generate these methane radicals. Now we can form several products after this initial reaction or initiation. We can propagate we can propagate or continue to make these radicals and terminate these radicals by forming our radical couplings. That is, we can either reform our chlorine, or we can form these symmetrical alkyl groups. But a couple of the major products will be, and this will be plus 2 hydrogens. But some of our major products will be the hydrogen plus the chloride, and our methane radical plus the chloride. And this process tends to favor the production of our substituted alkane, because this is a primary carbon radical, and versus the halide and the symmetrical alkyl product. So our primary carbon radical is our major product. And if this was a secondary, this would be, let me put it down here, this is a secondary because it's hooked to 2 carbons. Alright, so this would be our secondary carbon radical, and this actually is favored over our primary. And if we had a tertiary, which would look like this, we had a tertiary radical. This would be our most stable radical and would be more favored over secondary and primary. So we'll look at this again when we look at some of the tests for alkanes, alkynes, alcohols. The primary product is usually the one that produces the most stable radical, and tertiary is the most stable. Alright, so we'll be looking at these types of reactions, radical substitution and combustion in generating products of alkane and alkyne and alkene reactions.